The bedrock of reality itself might be unstable. We are taught that the proton, a fundamental piece of every atom, lasts forever. But what if that is a grand illusion? A silent, imperceptible decay could be happening all around us, a process so slow it has evaded detection for all of human history. Finding it would be the key to a grand unified theory, a single framework weaving all the forces of nature into one elegant tapestry. By the end of this, you will understand how this single discovery could rewrite the laws of physics and reshape future technology. We will journey into deep, underground laboratories where scientists wait to catch a glimpse of this cosmic transformation. How does it feel to question the permanence of everything you see? Everything in your world feels solid and permanent because of this simple, unshakable belief. The atoms in your body, the air you breathe, the ground beneath your feet, they all rely on the proton, a particle we are taught is eternal. Classical physics painted a picture of a stable, predictable universe where the building blocks of matter simply do not vanish. This idea is woven into the very fabric of our daily experience. We never see a chair or a mountain or a person suddenly disintegrate because their protons decided to decay. Our entire reality is built on the assumption of their steadfastness, but this permanence is a magnificent illusion, a trick of the timescale on which we live our brief lives. The rules change when we peer into the quantum realm and the vast stretches of cosmic time. Grand unified theories which attempt to merge all the fundamental forces of nature into one make a startling prediction. They suggest that the proton is not truly stable. It can and eventually will decay. The process is just so incredibly, unimaginably slow that it has escaped our notice for all of human history. This transforms our search from a simple scientific inquiry into a cosmic detective story. We are looking for a single, transformative event that might happen only once in a universe of particles over a span of time longer than civilizations. How do you catch a ghost that leaves a trace only once in a trillion lifetimes? This quest for unity is a deep human impulse, a drive to find one simple rule behind endless complexity. In physics, this ambition takes a breathtakingly specific form. It is the dream of grand unification, the attempt to weave three of nature's fundamental forces into a single, elegant tapestry. These are the electromagnetic force which gives us light and holds our atoms together, the weak nuclear force which governs certain types of radioactive decay, and the strong nuclear force, the immensely powerful glue that binds the cores of atoms. Right now, our best theories describe these forces as separate languages, each with its own rules and particles. Grand unified theories, or GUT, propose that these are merely different dialects of one fundamental tongue, a language spoken by the universe in its first moments of existence. Think of it like this: you have English, Spanish, and Mandarin. They seem completely different with unique sounds and structures, but linguists can trace them all back to a common ancestral language. Grand unification does the same for the laws of physics. It seeks the primal root from which all forces sprang. In that hot, dense beginning, the universe was a place of ultimate simplicity and symmetry. There was only one superforce and one family of particles. As the cosmos expanded and cooled, this perfect symmetry shattered, like a pane of glass cracking as it hardens. The one force fractured into the three distinct forces we see today. This elegant idea does more than just tidy up our textbooks. It makes concrete, testable predictions. To make the math of unification work, these theories require the existence of new, incredibly heavy particles that we have never seen. And it is the ghostly influence of these particles that allows for a proton to decay. They provide a hidden pathway, a secret tunnel through the bedrock of reality for a proton to transform into something else. The decay we search for is a faint echo from that age of unity, a whisper from a time when the cosmos was far simpler. This quiet transformation begins with the quarks locked inside every proton. You can think of a proton not as a single solid ball, but as a tiny, frantic community of three quarks bound together by the strong nuclear force. They are the fundamental residents of the atomic nucleus. Grand unified theories introduce a startling new rule to this community. They suggest that a quark can, on very rare occasions, change its identity entirely. It can transform into a different, much lighter particle like a positron or a meson. This is not a simple rearrangement. It is a fundamental alteration of the proton's very substance. When one quark undergoes this metamorphosis, the delicate balance holding the proton together is shattered. The proton simply ceases to be. It does not explode. It does not glow. It just quietly winks out of existence, its mass converted into pure energy and lighter particles that fly away. The predicted lifetime for this event is almost beyond human comprehension. Many theories suggest a proton might live for 10 to the power of 34 years or even longer. To grasp that number, consider the current age of our universe is a mere 13.8 billion years. That is 10 to the power of 10 years. A proton's potential lifespan is a 1 followed by 34 zeros. It is a timescale so vast that all of recorded human history is less than a single heartbeat in comparison. We are searching for an event that might happen just once in a tank containing more protons than there are stars in the observable universe over the course of an entire year. This is the ultimate test of patience, a hunt for a single falling leaf in an infinite, timeless forest. Catching a proton in the act of decay is not just about ticking a box in a physics textbook. It would be a discovery that shatters our current understanding of the universe on a fundamental level. Our best model of particle physics, called the Standard Model, is a masterpiece of prediction and precision. But it explicitly states that the proton is stable, that it cannot decay. To see one vanish would be to watch the Standard Model break before our eyes. This single observation would be our first direct, undeniable piece of evidence for a reality that exists beyond that model. It would be like finding a single, perfect fossil that proves an entire chapter of evolutionary history we had only ever guessed at. That fossil is grand unification. A detected proton decay would be the smoking gun, the definitive proof that these theories are not just elegant math, but a true description of how the cosmos operates. It would validate the beautiful idea that our universe began in a state of perfect symmetry. More than that, it would give us a unique window into the universe's first moments. We cannot build a time machine to travel back to that searing dawn, but we can build a detector. The rate and manner of a proton's decay would be a message, a tiny data packet sent across 14 billion years. It would tell us about the incredible energies and the specific particles that existed when all forces were one. This is the ultimate goal, a theory of everything. A single, coherent framework that explains every force and every particle, from the immense gravity that shapes galaxies to the quirky rules of the quantum world. Finding proton decay would be the crucial first step on that path, and what lies at the end of that path, the implications stretch far beyond pure knowledge. Every time humanity has peeled back a layer of reality, new technologies have emerged. Understanding electromagnetism gave us the electric grid and global communication. Taming the nucleus gave us nuclear power. Unlocking the principles of grand unification could reveal entirely new forms of energy generation, harnessing processes that power the stars themselves. It could redefine our relationship with matter, allowing us to manipulate the fabric of reality in ways we can barely conceive. This search is about more than rewriting textbooks. It is about uncovering the ultimate fate of everything. If protons decay, then all matter is inherently transient. Every star, every planet, every structure in the universe is living on borrowed time. This gives a profound, if distant, expiration date to the cosmic order. Yet in that ephemeral nature lies a deeper truth about the universe we call home, a truth we are only just beginning to grasp. The sheer scale of this challenge is almost a paradox in itself. We are hunting for an event so rare that its predicted timescale defies all everyday intuition. If a proton does decay, its half-life could be 10 to the 34th years or more. This number is not just large, it is a realm beyond human experience. To put it in perspective, if you filled a swimming pool with water, you would be holding an almost uncountable number of protons. Yet, even in such a vast crowd, you might only expect a single proton to decay over the course of an entire year. It is the ultimate needle in a cosmic haystack, where the haystack is the size of a planet, and the needle appears only once in a blue moon. So how do you design an experiment to catch such a ghostly flicker? The answer lies in building a bigger haystack and making it impossibly quiet. Scientists must construct detectors of staggering size, vessels containing thousands or even tens of thousands of tons of ultra-pure water or other materials. Every single additional ton of matter means more protons, which increases the odds, however slightly, of witnessing that one precious transformation. But size alone is not enough. The real enemy is noise. Our world is constantly bombarded by cosmic rays, high-energy particles from space that constantly zip through our bodies and the Earth. In a proton decay detector, the signature of a cosmic ray collision can look almost identical to the signal of a decaying proton. To have any hope of seeing the real event, you must eliminate every other possible source of interference. This is why these monumental experiments are built deep underground, housed within mountains or in old mines, where thousands of feet of solid rock act as a natural shield, absorbing the cosmic chatter from above. Even the materials of the detector itself must be crafted with obsessive care, selected for their incredible purity to ensure they are not slightly radioactive and generating their own background noise. The entire setup is a temple of silence, a place built to listen for a whisper that has not been heard since the universe began. This immense effort is all focused on waiting for a single, perfect flash of light in the profound darkness. Buried a kilometer beneath the Japanese Alps, inside the silent darkness of a working zinc mine, rests a cathedral of science. This is the Super Kamiok and detector, a chamber so vast it could comfortably hold a 10-story building. Its primary component is a staggering 50,000 tons of the purest water on Earth, a volume so clear and clean it acts as a perfect window into the subatomic world. The water is contained within a cylindrical stainless steel tank, its walls lined with over 13,000 golden orbs, each one a hypersensitive light detector called a photomultiplier tube. These are the unblinking eyes of the experiment, waiting in the absolute dark for a single, specific kind of flash. They are not looking for a simple spark. They are waiting for the ghostly blue signature of Cherenkov radiation. This is the crucial clue that could betray a proton's demise. When a proton decays, it does not vanish without a trace. It transforms into lighter, faster particles. If one of these decay products, like a positron or a muon, travels through the water faster than light itself can move in that same water, it creates a shockwave of light. Imagine a jet plane breaking the sound barrier and creating a sonic boom. This is the light equivalent, a luminous boom. The particle pushes through the water, distorting the electromagnetic field around it and releasing a faint, beautiful cone of blue radiation. This is not a bright flash you could see with your naked eye. It is an incredibly faint, fleeting pulse, but to the 13,000 golden eyes staring into the darkness, it is as clear as a firework in a night sky. They capture this ring of blue light, its precise shape and intensity, allowing scientists to reconstruct the entire event. They can determine what kind of particle caused it, its energy, and its direction of travel. This is how they distinguish a potential proton decay from the constant background noise of other cosmic interactions. The entire colossal apparatus is a trap, set to catch the ephemeral blue glow of a single transformation, a whisper of light that speaks of the universe's deepest secrets. So in the profound silence of that 50,000-ton water tank, what does the death of a proton actually look like? It begins not with a bang, but with a perfect geometric ring of light. Picture the instant a proton at the heart of an oxygen nucleus spontaneously transforms. It shatters into lighter particles, and one of them, a positron, is flung away at a speed so immense it breaks the light barrier in water. This creates a conical shockwave of blue Cherenkov light, much like the V-shaped wake a speedboat etches on a still lake. This cone of light expands outward until it strikes the wall of the detector. There it appears not as a diffuse glow, but as a sharp, luminous ring projected onto the array of golden photomultiplier tubes. That single, perfect ring is the ultimate prize, the smoking gun signature. It is a fully contained event, its light pattern clearly pointing back to a single point of origin within the water, but the universe is rarely so clean. The real challenge is that this pristine signal has competition. The same detector is constantly peppered with neutrinos, ghostly particles that pass through the entire Earth almost unnoticed. A neutrino can bump into a proton or an electron in the water, creating its own faint Cherenkov ring. The key to the hunt is in the subtle differences. A neutrino interaction often looks messy, perhaps producing multiple rings or a track that enters the detector from the outside. The signature of a true proton decay, however, would be a single, beautiful ring that appears from nowhere, its energy perfectly contained within the tank with no incoming track. It would be a burst of light born in the utter darkness, a self-contained star flickering to life and dying in a microsecond. Scientists have spent decades staring at their data, searching for that one perfect ring among countless imitators. Finding it would be like hearing a single, pure note of a specific frequency rise from a cacophony of cosmic noise, a note that sings of a unified universe. After decades of patient waiting in the profound dark, that single, perfect ring of light has yet to appear. This absence of a signal is not a silent failure, but a loud and clear message from the universe. The null result is itself a profound discovery. It has already reshaped our map of fundamental physics by telling us where not to look. The simplest, most elegant versions of grand unified theories predicted a proton half-life that our most sensitive experiments should have easily seen by now. The fact that they have not means those beautiful, straightforward models are almost certainly wrong. We have been guided by their elegance, but the universe has demanded greater complexity. This non-observation pushes the predicted half-life of the proton to even more staggering numbers, perhaps 10 to the 35th years or longer. Each year that passes without a decay is another piece of data that forces our theories to evolve, to become more nuanced and more powerful. It is a process of elimination on a cosmic scale, where every dead end we confirm brings us closer to the true path. Think of it as a grand treasure hunt where every empty chest you open, while disappointing in the moment, tells you the real treasure must be hidden somewhere even more extraordinary. The search has become a dialogue with nature, and nature is patiently teaching us that its ultimate secrets are buried deeper than we first imagined. Yet the silence from Super Kamiok and is not an end but a call to build something even greater. The next chapter in this cosmic hunt is already taking shape, a colossal successor known as Hyper Kamiokande. Its design is a testament to the scale of the challenge. Imagine the vast volume of Super Kamiokande, that cathedral of water holding 50,000 tons. Now multiply that by a factor of 8, Hyper Kamiokande, and will contain a staggering 260,000 tons of ultra-pure water, a volume so immense it could fill 100 Olympic swimming pools. This is not merely an upgrade, it is a leap into a new realm of sensitivity. The sheer number of protons in this new detector is almost beyond comprehension. More protons mean more opportunities, dramatically increasing the odds of finally witnessing that single, elusive decay. But size is only part of the equation. The next generation of golden eyes lining the tank will be vastly improved. they will be more sensitive, able to detect fainter and more precise patterns of Cherenkov light. This enhanced vision will allow scientists to distinguish with even greater certainty between a true proton decay and the background chatter of neutrino interactions. Think of it as upgrading from a standard microphone to a sophisticated array that can pick out a single, specific voice from a roaring crowd. If a proton decays within its vast volume, hypercamioc, and will not just see it, it will capture the event with unparalleled clarity, leaving no room for doubt. The goal is clear: to either catch the proton in the act or to push the known limits of its stability to numbers so grand they will challenge the very edges of theoretical physics. This monumental machine is our species' most determined effort to answer a fundamental question about the fabric of reality. Will we finally see the blue ring that confirms our universe began in unity, or will the continued silence guide us toward an even more profound and unexpected truth? The hunt is about to enter its most ambitious phase. While hypercamioc and scans vast volumes of water for rings of light, a parallel quest is unfolding deep beneath the plains of South Dakota. Here, scientists are preparing a different kind of trap, one that does not listen for faint whispers of light, but instead freezes a moment in time to examine it in 3 dimensions. This is the Deep Underground Neutrino Experiment, or DUNE, and its core technology is a substance that seems almost alien: liquid argon. At temperatures colder than the void of outer space, argon gas condenses into a clear, dense liquid, a perfect medium for catching the subtlest of subatomic events. Instead of looking for rings on a wall, DUNE detectors act as the most sophisticated cameras in existence. They are called liquid argon time projection chambers. Imagine a vast tank filled with this ultra-pure, frigid liquid. When a particle like a neutrino, or the product of a potential proton decay, passes through, it bumps into an argon atom and knocks electrons loose. This is the beginning of the magic. A strong, uniform electric field is applied across the entire tank, which acts like an invisible wind. This electric wind gently pushes the freed electrons across the chamber without blurring or distorting them until they hit a finely segmented wire plane. As each electron arrives at the wires, its position and the precise time of its arrival are recorded. By meticulously tracking the drift time and location of thousands of these electrons, the detector can reconstruct the original particle's path in breathtaking detail. The result is not a simple ring, but a full, 3-dimensional movie of the interaction. You can see the precise millimeter by millimeter track of every particle created in a collision, as if you were watching a subatomic ballet from the front row. For proton decay, this 3-dimensional clarity is a game changer. The signature of a proton's demise is often complex, producing multiple particles that fly off in different directions. In a water Cherenkov detector, these can overlap and create a messy, ambiguous pattern of light. But inside DUNE liquid argon chamber, each of those particles would paint its own distinct, crisp trail in the 3-dimensional reconstruction. Scientists could follow each path back to its exact point of origin, confirming that they all began at the same instant from a single, stationary point deep within the argon. This ability to see the event from every angle, to untangle a web of particles with perfect spatial resolution, offers a powerful and complementary method to confirm what a single ring of light can only suggest. It is the difference between hearing a single, beautiful note and being able to see the entire orchestra that created it. This dual approach with hypercamioc and immense scale and DUNE exquisite resolution means we are not just building a bigger trap, but a smarter one, designed to recognize the truth no matter what form it takes. Neutrinos are the ultimate double agents in this cosmic investigation. They are both the most frustrating source of noise and a precious signal, a duality that makes the search for proton decay uniquely complex. Every second, trillions of these ghostly particles from the sun and distant cosmic events pass straight through the Earth and through you without a trace. inside a detector like Super Kamiok, and however they sometimes stop being ghosts, a neutrino can very rarely collide with an electron or a nucleus in the water, creating a flash of Cherenkov light that looks hauntingly similar to the signal scientists are desperate to find. This is the background noise, a constant, faint drizzle of false alarms that makes finding the one true event feel like listening for a single unique word in a crowded, bustling city. Filtering out this neutrino background requires an almost supernatural level of pattern recognition. Researchers must become connoisseurs of light rings, analyzing every tiny detail of the signal, its sharpness, its energy, and its geometry, to separate the mundane neutrino interaction from the revolutionary proton decay. Yet in a beautiful twist, this same challenge reveals an incredible opportunity. To hunt for a proton decaying once a year, you must build a machine so sensitive it becomes the perfect observatory for the neutrinos themselves. These experiments, designed to find one impossibly rare event, have become our foremost windows into the neutrinos' mysterious world. They have captured neutrinos from the sun, from supernova, and even from the violent hearts of distant galaxies. This is not a side effect, it is a core part of the quest. The physics of grand unification and the nature of neutrinos are deeply intertwined. Many grand unified theories naturally predict that neutrinos must have a tiny amount of mass, a property that was only confirmed in recent decades. The way neutrinos oscillate, changing from one type to another as they travel, is a direct consequence of this mass and a vital clue to the physics operating at those incredible unification energies. By studying these oscillations with immense precision, we are indirectly testing the very theories that predict proton decay. Each neutrino detected and analyzed is another piece of the puzzle, helping us refine our models and understand what a true proton decay signal should really look like. The search for a vanishing proton and the study of a passing neutrino are two sides of the same coin, a unified effort to read the universe's most fundamental script. This profound link between a proton's stability and the universe's very existence brings us to one of cosmology's greatest puzzles. Why is there something rather than nothing? More precisely, why is the cosmos filled with matter, with stars and planets and us, when our best theories suggest it should have been born with equal amounts of matter and antimatter? If that perfect balance had held, the two would have annihilated each other completely in a burst of pure energy, leaving behind a vast, empty void. The simple, startling fact that we are here means that for every billion pairs of matter and antimatter particles created in the Big Bang, one single matter particle survived. That tiny 1 in a billion excess is everything we see. This is the mystery of baryon asymmetry, and the search for proton decay is directly tied to its solution. Grand unified theories do not just predict a pathway for protons to die, they also provide the very conditions needed to explain this primordial imbalance. In those first moments of ultimate unity, the heavy particles predicted by GUTs could have decayed in a way that was not perfectly symmetrical. They might have produced just a few more quarks, the building blocks of protons, than antiquarks. Over time, the antiquarks found their counterparts and annihilated, while the leftover quarks went on to form all the atoms in the universe. This means that every proton we are made of is a survivor from that ancient asymmetric war. A detected proton decay would be far more than just observing a rare event. It would be like finding a fossil from that exact process. The specific way a proton decays, the particles it turns into, would reveal the fingerprints of those primordial, asymmetry-creating mechanisms. It would tell us not only that matter is temporary, but also why it was ever created in the first place. The hunt for a vanishing proton is, at its heart, a search for our own cosmic origin story, a quest to understand why there is a universe we can call home at all. The elegant idea of supersymmetry offers a beautiful escape from the proton decay puzzle. This theory proposes a profound and hidden symmetry woven into the fabric of reality, where every known particle has a secret, super-heavy twin. The electron would be partnered with a selectron, the quark with a squark, and the photon with a photino. These supersymmetric particles are not just a theoretical curiosity, they are a potential key to stabilizing the universe we see. In the simplest grand unified theories, the math allowed protons to decay far too quickly, a prediction clearly at odds with our existence. Supersymmetry steps in and tames these calculations. The presence of these superpartners changes the high-energy equations, adding new pathways and interactions that can push the proton's predicted lifetime far beyond our current experimental reach, into the safer territory of 10 to the 35th years or more. This does not kill the dream of unification, it refines it. Supersymmetry suggests that protons do decay, but at a rate so excruciatingly slow that it perfectly explains why we have not seen it yet. The hunt for proton decay is therefore a direct test of this elegant symmetry. Every year that passes without a decay in our detectors is not just a limit on the proton's life, it is a constraint on the possible masses of these superparticles. If supersymmetry is real and these particles are relatively light, then proton decay should be just around the corner for our next generation of experiments. If it remains elusive, it tells us that the supersymmetric world, if it exists, lies at energies far higher than we initially hoped. This creates a powerful link between the silent, waiting detectors deep underground and the violent, high-energy collisions at machines like the Large Hadron Collider. There, physicists are actively trying to create these superpartners by smashing protons together with unimaginable force. They are hunting for a missing energy signature, a sign that a heavy supersymmetric particle was created and carried away energy undetected. So far, the colliders have also seen nothing. The continued silence from both fronts, the deep underground labs and the particle colliders, is speaking to us in unison. It is telling a consistent story that the hidden layers of reality are more complex and perhaps more distant than our most elegant theories presumed. We are not just searching for one particle's death, but for an entire shadow universe of particles that could redefine stability itself. The silence from our deepest detectors has not closed the book on proton decay, but has instead opened it to more exotic chapters. While classic grand unified theories provide the most elegant pathway, other profound ideas in theoretical physics suggest the proton might vanish in ways we have barely begun to consider. Imagine the fabric of our universe not as a simple, four-dimensional stage, but as a structure with tiny, curled-up extra dimensions far smaller than an atom. In such a cosmos, gravity, which feels so weak to us, might actually be as strong as the other forces, its true power diluted as it spreads into these unseen realms. Within this breathtaking framework, a proton could potentially decay by leaking into these extra dimensions, or by creating a microscopic black hole that instantly evaporates. The signature of such an event would be utterly bizarre, a spray of particles unlike anything predicted by standard models. String theory, an attempt to describe all particles as tiny, vibrating strings, also permits protons to decay. The stability we observe might simply be a result of our universe residing within a specific, fortunate configuration of these strings, a cosmic accident that could, under the right conditions, be undone. This pushes the search beyond looking for a single, perfect ring of light. We must now also be alert for exotic decay channels, where a proton might not just produce a positron and a meson, but something far stranger, like a trio of neutrinos or even a yet undiscovered particle. The detectors are not just listening for one specific note anymore, they are listening to the entire symphony of the subatomic world, ready to identify any discordant sound that breaks the established rules. This uncertainty is what keeps the field so vibrantly alive. The continued non-observation is not a dead end, but an invitation to think more wildly, to consider that the bedrock of reality might be crumbling in ways we are only now learning how to see. These underground temples of science form a global network, a silent alliance buried deep within the Earth's crust. In the darkness of an old nickel mine in Canada, 2 kilometers below the surface lies Snarlab. To reach it, you descend in a cage elevator, plummeting into the rock for several minutes before stepping out into a world of impeccable cleanliness. Every scientist must shower and change into lint-free clothing, for even a single speck of dust can carry enough natural radioactivity to ruin the search for a single proton's decay. Across the Atlantic, nestled within the Gran Sasso mountain range in Italy, the Laboratory Nazionale del Gran Sasso, or LNGS, is another fortress against interference. Here, 1.4 kilometers of solid rock shield delicate experiments, allowing them to listen for the universe's quietest signals. And back in North America, at the Sanford Underground Research Facility, or SURF, in South Dakota, the old Homestake gold mine has been reborn as a frontier of physics, hosting the future home of the Dune experiment. This global collaboration is not a competition, but a shared quest. Each lab leverages its unique geology and infrastructure to contribute a different piece to the puzzle, their collective data forming a single, unified picture. The reason for this extreme depth is a constant, invisible rain from the sky. Cosmic rays, high-energy particles from distant supernova and black holes, bombard our atmosphere every second. At the surface, these particles create a cacophony of nuclear interactions, a deafening background static that would completely drown out the faint, singular pop of a decaying proton. Going deep underground is the only solution. The thousands of feet of rock above these laboratories act as a colossal filter, absorbing nearly all of this cosmic noise. It is the ultimate quiet room, a place where the faintest whisper from the quantum world can finally be heard. Without this profound silence, the search would be impossible, like trying to hear a pin drop in the middle of a hurricane. This background noise is the true adversary in the hunt for proton decay. Even a kilometer underground, the silence is not absolute. The most persistent intruders are muons, the heavy, penetrating cousins of electrons. They are born in the upper atmosphere when cosmic rays smash into air molecules, and they rain down upon the Earth in a relentless downpour. Though the rock above filters out most, a few muons per second still punch through into the largest detectors. Each one creates a brilliant, unmistakable streak of Cherenkov light as it crosses the tank, an event so energetic it can mimic or even mask the delicate signature of a proton's demise. To combat this, experiments employ sophisticated muon veto systems. Arrays of detectors placed outside the main tank act like a security perimeter, tagging any particle that enters from the outside. If the golden eyes inside the water see a flash at the exact same moment the outer fence is triggered, the event is instantly flagged as background noise and discarded. It is a constant process of digital triage, separating the cosmic tourists from the residents, but the challenge runs even deeper than outside interference. The very materials of the detector itself can betray the search. Every substance on Earth contains trace amounts of radioactive elements like uranium, thorium, and potassium-40. These atoms spontaneously decay, releasing alpha particles, beta particles, and gamma rays that can bounce around inside the water, creating faint, random flashes of light. To minimize this internal chatter, scientists must become masters of purity. The stainless steel for the tank is specially smelted underground to avoid cosmic ray activation. The water is filtered to an almost impossible standard, stripped of every contaminant. The photomultiplier tubes are built with ultra-pure glass and low radioactivity ceramics. Every component is selected and tested to ensure its internal radioactivity is lower than the already minuscule natural background. This is a war fought at the atomic level, a battle for the quietest environment ever created. And then there are the neutrinos. These ghostly particles from the sun and distant supernova pass effortlessly through the rock and the detector walls, creating a constant, low-level drizzle of interactions that look hauntingly similar to the signal being sought. This is the most insidious background of all because it cannot be blocked or shielded against. The only way to overcome it is through sheer analytical brilliance. Researchers must write algorithms that can distinguish the specific light pattern of a proton decay from the myriad of neutrino signatures, a task of pattern recognition so fine it is like identifying a single, unique snowflake in a blizzard. This monumental effort in background reduction is the unseen heart of the experiment. For every year of data collected, countless more are spent in meticulous cleaning, sifting through quadrillions of events to find the one that stands completely alone, a burst of light with no explanation other than the quiet end of a proton. Even the quietest rooms in the universe are filled with a chaotic symphony of data. Our detectors capture not just a few events, but a continuous, overwhelming torrent of information, a digital flood of light patterns and particle tracks measured in petabytes. Sifting through this ocean for one specific, perfect signature is a task that defies human capability. This is where a new partner enters the hunt, one that can perceive patterns in the noise that are invisible to us. Artificial intelligence and machine learning are now the essential co-investigators in the search for proton decay. These are not simple algorithms following preset rules. They are neural networks, complex digital brains modeled loosely on our own, trained on millions of simulated events. Scientists feed these AI systems countless examples, teaching them the precise digital fingerprint of a true proton decay ring, the messy splash of a neutrino interaction, and the sharp streak of a cosmic muon. The machine learns the subtle language of the detector, discerning features a human eye would never catch. It might notice a specific asymmetry in the light distribution, or a tiny, consistent timing delay between certain photomultiplier tubes that betrays a particle's origin. Over time, the eye develops an almost supernatural intuition for the data. It can process a year's worth of information in a fraction of the time, flagging only the most promising candidate events for a physicist's final review. This is not about replacing human curiosity, but augmenting it with a new kind of perception. Think of it as trying to find a single, unique seashell on a beach that stretches for thousands of miles. A human could walk that beach for a lifetime and see nothing, but an eye flying overhead and analyzing the color, shape, and texture of every single shell simultaneously can instantly pinpoint the one that matches the description. This fusion of futuristic technology and fundamental physics is reshaping the entire endeavor. It allows us to ask more nuanced questions of our data, to test more exotic decay models, and to listen more intently than ever before to the silent, waiting universe. The hope is that this powerful new lens will finally spot the one flash we have been waiting for, the signal that has been hiding in plain sight all along. This search for the universe's most elusive signal is quietly reshaping our own world. The very tools forged to catch a single decaying proton are now spinning off into technologies that touch our daily lives, proving that the quest for pure knowledge often builds the bridge to practical wonder. Consider the immense volumes of ultra-pure water required for detectors like Super Camiok, and this is not just filtered water, it is a substance of almost impossible clarity, stripped of every mineral, every ion, every trace of radioactive dust. To achieve this, scientists had to become pioneers of purification, developing systems that far surpass anything used in conventional treatment plants. These advanced filtration and deionization technologies are now finding direct applications in creating ultra-pure water for the semiconductor industry, where the tiniest impurity can ruin a microchip, and in pharmaceutical manufacturing, where water purity can mean the difference between a safe drug and a contaminated one. The same relentless drive for atomic-level cleanliness that protects a physics experiment from background noise is now helping to build the next generation of electronics and medicine. Then there are the eyes of the experiment, the thousands of hypersensitive photomultiplier tubes. These are not simple light bulbs, they are masters of amplification, capable of detecting a single photon and multiplying its signal millions of times in a heartbeat. This technology, honed in the darkness of underground labs, is revolutionizing medical imaging. Positron emission tomography, or PET scans, rely on detecting pairs of gamma rays produced inside a patient's body. The latest generation of PET scanners incorporates technology directly descended from particle physics, using advanced light sensors to pinpoint the origin of those rays with breathtaking precision, allowing doctors to locate tumors with a clarity that was once a fantasy. This gives physicians a powerful window into the inner workings of the human body, all thanks to a device perfected to watch for the blue glow of a dying proton. But perhaps the most profound spin-off lies in how we think. The challenge of processing a deluge of data from these experiments, of finding one meaningful pattern in a quadrillion meaningless ones, has forced a revolution in computing. The machine learning algorithms and artificial intelligence systems developed to hunt for proton decay are not locked away in a physics lab. They are the same tools now used to predict complex weather patterns, to discover new materials by simulating atomic structures, and to analyze the human genome for hidden links to disease. The need to understand the universe forced us to teach machines how to see, and now that machine vision is helping us understand ourselves. This is the beautiful, unplanned dividend of curiosity-driven science. We dig deep into the Earth to answer a question about the cosmos, and along the way we invent better ways to heal, to build, and to see. The search for a unified theory might seem like a distant, abstract dream, but its pursuit is already building a more advanced and insightful world, one pure drop of water, one single photon, and one brilliant algorithm at a time. This quiet decay, if real, rewrites the destiny of every star and galaxy. We are forced to confront a universe where matter itself has an expiration date, a future so distant it defies all human scales of time. The cosmos we know, with its brilliant galaxies and swirling nebulae, is built upon the steadfastness of the proton. It is the anchor for every atom, the unchanging bedrock of physical reality. But if that bedrock is slowly, imperceptibly crumbling, then every structure we see is ultimately temporary. This leads us to a profound and sobering cosmic forecast, a fate known as the heat death of the universe. Imagine the very last stars have finally burned out, their furnaces cold for trillions upon trillions of years. Black holes, the last great structures, have themselves evaporated through a process theorized by Stephen Hawking. The universe is a dark, expanding void, filled only with a thin, cooling soup of radiation and the scattered remnants of dead stars. In this epoch, long after the last light has gone out, the process of proton decay becomes the final act. One by one, the nuclei of every remaining atom, the frozen ashes of long-dead suns, begin to dissolve. A proton inside a lone iron nucleus, a relic from a forgotten supernova, spontaneously transforms. It releases its energy and vanishes, then another does the same, over timescales that make the current age of the universe seem like a single blink. All complex matter unravels at its most fundamental level. The universe becomes a sea of leptons and photons, a formless, ultra-cold fog where no atom can ever form again. No new stars will be born, no new planets will coalesce. The engine of complexity and structure runs down to a final, irreversible halt. This is not a violent end, not a cataclysm or a collapse. It is a slow, gentle fading into maximum entropy, a state of perfect and eternal equilibrium where nothing ever happens again. The philosophical weight of this is immense. It tells us that the cosmos is not on a cyclical path of eternal rebirth, but on a one-way journey toward silence. The transient nature of matter, revealed by a single subatomic event, dictates the ultimate fate of all we see. Yet within this ephemeral existence lies a strange and powerful beauty. Our brief, vibrant moment in the cosmic timeline, this era of light and life and discovery, becomes infinitely more precious precisely because it is temporary. We are a flicker of consciousness in the long, dark slide toward equilibrium, a flash of brilliance against an unimaginably vast and quiet canvas. The search for proton decay is not just about how the universe began, but about how it will end, giving profound meaning to the fleeting story unfolding right now. The profound silence from these next-generation detectors would speak with its own thunderous voice. If Hyper-Kamiokande and Dune, with their unprecedented scale and precision, still find no trace of a decaying proton, the implications would be as revolutionary as a discovery itself. This enduring null result would be a monumental conclusion, forcing a fundamental pivot in our quest for a unified theory. The most elegant and promising grand unified theories, the ones that have guided physics for decades, would be decisively ruled out. Their beautiful mathematical frameworks, which so neatly predicted a decay we should have seen by now, would have to be abandoned or radically transformed. This is the rigorous and sometimes brutal process of science at work. It is not a failure, but a necessary pruning of the tree of knowledge, cutting away beautiful but incorrect branches so that new, more robust ideas can grow. The path forward would lead us into even more exotic and speculative territory. We might be forced to consider that the scale of unification is far grander than we thought, requiring energies so high they are permanently beyond our direct observation. Or perhaps the stability of the proton is safeguarded by a new, unknown principle of nature, a conservation law we have not yet conceived. This scenario would elevate the proton from a simple particle to a profound cosmic mystery in its own right. Its stubborn refusal to decay would become one of the most important unsolved problems in all of physics, a beacon pointing toward a deeper, more complex layer of reality. The search would not end, it would evolve. We would be compelled to ask different questions, to design even more clever experiments, and to question our most basic assumptions about matter, time, and symmetry. The absence of a signal is itself a powerful signal, guiding us away from dead ends and toward a truth that is, for now, just beyond the horizon of our imagination. You do not need a PhD or a lab coat to join this grand cosmic search. The hunt for proton decay is no longer confined to the silent halls of underground science. It is a quest that now reaches directly into your home. A new wave of citizen science projects is shattering the walls of the laboratory, inviting everyone with curiosity and an internet connection to become a co-investigator in one of physics' greatest mysteries. These initiatives recognize that the greatest untapped resource is not just computing power, but human perception, our innate ability to recognize patterns that even the most advanced algorithms might miss. Imagine the torrent of data flowing from detectors like Hyper-Kamiokande, a river of digital information containing millions of potential events. While artificial intelligence does an incredible job of filtering, there is still a role for the human eye, for that spark of intuition that can spot an anomaly a machine was not trained to find. Platforms like Zooniverse host projects where you can view actual data from particle physics experiments. You might be presented with a simulated collision event or a pattern of light rings and asked to classify what you see. Is it a clean, single ring, a messy splash, a straight muon track? Each classification from a volunteer helps train the machine learning systems to be smarter and provides a crucial double check on the AI's work. You become part of a global team, a distributed network of minds working in concert to sift through the universe's raw data. Your click could be the one that flags a candidate event that leads to a monumental discovery. This is not a simulation, it is real data, and you are helping to analyze it. But participation does not stop at data analysis. The very existence of these monumental experiments depends on public understanding and support. You can become an ambassador for curiosity itself by simply learning about this research and sharing its profound questions with others. you help build a culture that values fundamental exploration. Discussing why we dig deep underground to ask questions about the beginning of everything sparks a vital conversation about our future. Advocacy for science funding at local and national levels is what ensures that projects like Hyper-Kamiok and Ndune can be built. These are not cheap endeavors, they are investments in the foundational knowledge that has, time and again, seeded the technologies of tomorrow. Your voice, telling the story of why this search matters, helps secure the resources for the next generation of explorers. This is how we collectively shape the technological landscape for our children and grandchildren. The quantum computer, the new energy source, the medical imaging breakthrough of 2050, they will be built on the basic research we choose to support today. By engaging as a citizen scientist, you are not just a spectator to history, you are an active participant in writing the next chapter of our cosmic story, ensuring that the search for unity continues to illuminate the path forward. The coming decade will transform our silent listening posts into roaring engines of discovery. By the middle of the 2030s, both Hyper-Kamiok and the Deep Underground Neutrino experiment are scheduled to be fully operational, their immense eyes open to the cosmos. This is not merely an incremental step forward, it is a qualitative leap into a new realm of sensitivity. For the first time in human history, we will have instruments powerful enough to either definitively catch the proton in its active decay or to push its potential lifetime so far into the future that it forces a complete reimagining of reality's laws. We are entering a decisive era, a narrow window in time where a single flash of light or a perfectly reconstructed particle track could answer a question as old as physics itself. The timeline is set, the engineering marvels are underway, and the global scientific community is holding its breath. This period, spanning the next 10 to 15 years, represents our best and possibly last clear shot at a classic grand unified theory for a generation. The stakes could not be higher. We are poised at the edge of two radically different futures. In one, a crisp blue ring appears in Hyper-K's vast water tank, or a stunning three-dimensional movie of a proton's disintegration plays out in Dune liquid argon. Either event would trigger a celebration rivaling the discovery of the Higgs boson, instantly catapulting our understanding of the universe to a new plane. Textbooks would be rewritten overnight, and a new era of fundamental physics, built on the confirmed foundation of unification, would begin. We would finally know that the forces we see as separate are truly one, and the dream of a theory of everything would feel tantalizingly within reach. Yet the other future is equally compelling and in its own way just as revolutionary. Imagine the year 2040 arrives, and after a decade of collecting data with these billion-dollar machines, the silence holds. No perfect ring, no unambiguous decay. The proton remains stubbornly, mysteriously stable beyond even our most heroic efforts to see it fall. This enduring null result would be a message from nature as profound as any discovery. It would be a clear declaration that our most elegant and beautiful theories are simply wrong. The universe is not as simple as we had hoped. This would not be an end to the quest, but a dramatic pivot into the unknown. It would force physicists to abandon well-trodden paths and venture into wilder, more speculative territory, perhaps involving extra dimensions or principles of stability we have not yet conceived. The next decade, therefore, is not just about finding an answer. It is about discovering which questions we should even be asking. Are we living in a universe whose unity is just within our grasp, or one that guards its ultimate secrets with a complexity we are only beginning to fathom? We are about to find out. The same deep underground labs built to catch a single vanishing proton have become our most versatile windows into the cosmos. While the ultimate prize remains elusive, these silent, shielded chambers are already revolutionizing astronomy by capturing the faintest signals from the universe's most violent and mysterious events. Their primary instrument for this is the neutrino, that same ghostly particle that creates a challenging background for the proton decay search. For neutrino astronomy, this background is the signal. The Sun, a continuous nuclear furnace, floods the Earth with trillions of neutrinos every second. Detectors like Super Kamiok and capture these solar neutrinos, allowing us to peer directly into the Sun's core and confirm our models of how stars shine. But the real cosmic watch begins when a star dies. In 1987, a predecessor experiment detected 24 neutrinos from a supernova in a nearby galaxy. It was the first and only time we have observed neutrinos from a stellar explosion beyond our own Milky Way, a 20-second burst that taught us more about a supernova's inner mechanics than centuries of optical astronomy. Today, these labs are on 24/7 supernova watch. Should a star in our own galaxy collapse, a coordinated global network of these detectors would be flooded with thousands of neutrino events hours before the light from the explosion even reached Earth, providing an automatic early warning system for the most spectacular light show in the galaxy. Beyond stellar life cycles, these facilities are on the front lines of the dark matter hunt. We know this invisible substance outweighs normal matter 5-to-1, shaping the very cosmos, yet we have no idea what it is. Deep underground, shielded from cosmic interference, experiments search for the hypothetical, incredibly rare collision between a dark matter particle and the nucleus of an atom in their detector. A single tiny recoil, a vibration in the absolute quiet, could unveil the nature of 85% of the universe's matter. This transforms the concept of an observatory. We are no longer just looking for the death of a single particle, but listening to the faintest whispers of the universe's entire history, from the nuclear heart of our nearest star to the cataclysmic death of distant suns and the invisible scaffold of reality itself. These laboratories, buried beneath mountains and rock, have become all-purpose cosmic ears, tuned to a frequency of reality we are only just beginning to hear. Our journey into the heart of matter reveals an epic quest spanning from the mind's purest mathematics to the Earth's deepest foundations. It began with a beautiful theoretical idea, a vision of a unified cosmos where all forces were one. This elegance demanded a price, the shocking instability of the very protons that build our world. To test this grand claim, we had to become architects of silence, building colossal cathedrals of water and liquid argon deep beneath mountains, shielded from the universe's constant noise. We forged new technologies of purity and perception, all to catch a single, ghostly flicker of blue light, an event so rare it might occur just once in a universe's worth of particles. This pursuit is about far more than confirming a particle's decay. It is a direct line to the universe's first moments, a test of its ultimate symmetry, and a key to understanding why we are here at all, the leftover matter from a primordial imbalance. The technologies born from this search, from ultra-pure filtration to advanced medical imaging and powerful artificial intelligence, are already reshaping our world, proving that the quest for fundamental understanding is the deepest wellspring of practical innovation. As Hyper-Kamiok and Ndune open their eyes in the coming years, we stand at a threshold. We are building machines to listen for a whisper from the dawn of time, to witness a transformation that may happen only once in a tank holding more protons than there are stars in the sky. Stay curious, follow the progress of these monumental experiments, and take a moment to ponder the profound wonder of it all, that we, fleeting conscious beings on a small planet, have the audacity to build instruments to catch a cosmic heartbeat, a pulse that ticks once over timescales longer than existence itself.